Okay, welcome to day 4. What I'm hoping is that by the end of today, I will have completed all the tutorial stuff. I guess it depends not only on how many questions I get, but where those questions take us, because sometimes it's been adventurous. Um, okay, now, but before I get into all that, okay, I want to check my. I've been, I've It's kind of weird. Last night I increased my font size in here, but I'm not sure if that's reflected. Oh, yeah, I changed it from 20 to 22. Okay. We'll see how that goes. All right. Now, the various scripts that I assigned last time. Does anyone have any questions about those? Anyone have any difficulties with them? Yeah. I know a couple of you got them done back then, because if you weren't able to do them, um, we need to resolve that. So if you have a question about it now, that's fine, or you can ask me a question during one of the breaks, whatever, not particular, but just to make sure that everyone is at the same point. Okay. So I actually did have someone send me the files, but they're not even officially rolled in the class. So, just an interested viewer. Okay. So in other words, if I don't hear anything, I'm going to assume that you figured them out. If I am wrong, please correct me. Are we clear? Okay. Because I know how USM students are, even graduate students, about asking questions. Dang awful, with some exceptions. But there needs to be more. There needs to be enough exceptions so that that's a new rule. Okay. Now, just like when starting with MATLAB, you work with M files that are just scripts, basically commands that you would type at the prompt. And then you work your way up to functions. And that's what we're going to do right here. So I'm going to open a file that I had previously. Wait, I need to get myself in the right directory. Okay. So this is a simple function that will illustrate the mechanism. Okay. All right, I'm looking for convert temp. Here we go. Okay. Now, so here's our first example of a function, or also known as a method, in Python. So what we have here, just like in MATLAB, you would indicate a function by using the keyword function. Here we use the keyword def, short for define. So I'm defining function convertTemp. So convertTemp is the name of a function. And then, similar to syntax from MATLAB or other languages, you have parentheses, and then you have your input arguments. Here we only have one input argument, TF. TF refers to a temperature in Fahrenheit. And we're going to convert that to Celsius. That's what this function does. As with other statements like if, for, and while, after your argument list, you terminate with a colon. So then Python will know or your Python editor will know to indent on the next line. Now, what I have here is a multi-line comment, so begun with the 3 double quotes and ending with the 3 double quotes. That way, if I want to seek help on my function, just like you'd seek help on anything else in Python, this will actually work. Now, Actually, I haven't imported this yet, so I'm not sure if it'll work right now, but I will try it. Okay, I haven't imported it yet, and that's why we don't see it. So what I'm going to do is I'm going to import it from convert temp, import convert temp. Now, to explain this line, the first instance of convert temp, that refers to the file. The second instance refers to the individual function within the file. You can have as many functions as you like within a .py file. Now, there's a key difference. Okay, so let me go ahead and import this. Now, the difference between MATLAB and Python is, in MATLAB, all functions except the first are helper functions. So in other words, that cannot be accessed by other code from other files. In Python, all functions in the file can be imported. So in these simple examples, I'm making creating a file and putting just one function in it to illustrate something. But generally, that's not what's done. You would have a module or package that would be a single .py file that would have several functions defined in it. For example, to take the math package that has all the different math functions. So those could be defined in one file, and then you can import all of them or import select ones. Okay, so now that I've imported it, I can try getting help on it. So sure enough, the help string, the doc string that I put in here, is what is printed out here. And it also indicates what file it came from. And also signature indicates how you call it. That's very important, like what parameters are required. And then if the file came from it indicates that this is a function. Okay, so it's a good idea to provide this documentation if you're writing code that other people might use. So that way it's seamless. That you so people can get help on your stuff and what's in other packages. Okay. Now, as far as what the function does, so it carries out the computation, subtracting 32 and multiplying by 5/9 to convert this Fahrenheit temperature to Celsius. And here we have a return statement. Now, this is different from MATLAB, but it's closer to like other languages, like C and C++, where you're returning a certain expression. So in this case, I have my output, and that's what I'm returning. Now, here I'm only returning one item. You can actually return multiple items that are separated by commas. And on the left side, so when you call the function, you can have multiple items on the left side of the equals to accept those multiple returned items. So that's one thing that's quite convenient. So what's interesting is, unlike MATLAB, here you're not specifying up here what is returned. That just comes from your return statement. All right. So now that I've imported this function, I can go ahead and use it. So for example, similar to how you use functions in other languages. So sure enough, 212 in Fahrenheit is equivalent to 100 in Celsius. Okay. Now, another thing, and pretty much all languages behave this way. Notice that the function uses a variable called temp. Now, I'm going to set temp equal to 32. And then, so that's the freezing point in Fahrenheit. And now I'm going to call my function to convert that to Celsius, and predictably get 0. Now, what I want to point out here is this value of temp of 32 is passed in here, where now it's known as TF. So TF comes in equal to 32. And then in here, temp is set equal to that minus 32. So temp in here is equal to 0. So this temp is equal to 0. But if I go back out here and look at temp, it's still 32. So remember, each function, when it's called, has its own memory space. So variables that in here, that happen to have the same name as variables out here, are independent entities. So if you change one in here, it's not going to change out here. So as opposed to if I have an array in here and pass it in here, if I had changed, if TF was an array and I change it in here, which I'm not in this case, but if I was, that would actually take effect. Okay. Now, one thing I want to try, I didn't have this in my example, but I'm going to make an array of temperatures here. Well, I need to import NumPy first. Okay. Let's make a one-dimensional array. Okay. Like 5 temperatures. Oh, wait. I want random. Okay. So 5 temperatures. Now that's between 0 and 1. That's not very interesting. I'm going to multiply by 212. So now I have temperatures from 0 all the way to 212. Fahrenheit temperatures. Let's see what we got here. Okay, so we're kind of all over the place. And if I go ahead and pass that in, then now they're converted to Celsius. So, so that works out quite well. That because these operations, subtracting a scalar, multiplying by a scalar, are defined for vectors or matrices, NumPy ND arrays, just as for numbers. So convert temp can accept whatever you pass it. So in other words, it'll accept any object for which it's understood how to subtract scalars and multiply by scalars. So as long as that operation is defined, it can be passed as a parameter to this function. Now, with other operations that involve math functions like sine, cosine, etc., it's not so clean as in MATLAB. So that's something we'll come to a little bit later. Okay, now, so I have a simple function, or actually a simple pair of functions to assign you guys, working with the general function mechanism before we start looking at graphics, although I seem to be missing something here. Oh, okay. All right, I'll show that later. Yeah, I didn't have it in my note for some reason. Okay, now we know that the Python math package has sine and cosine, of course. So what I'd like you to do is this exploration. Okay, where you write your own functions that are called sine d and cos d that accept a single input argument, which we can assume is a number. And then go ahead and call, and you use Python's existing sine and cosine functions to, so the idea is the input is assumed to be in degrees. But sine and cosine, the native Python functions, just like in MATLAB or elsewhere, assume radians. So the idea is you got to take your value that's given to you that's assumed to be degrees, convert it to radians, then call sine and cosine on that, and then that is what you return. So now you go ahead and define these functions. So what I want you to do is, I'll put some comments in here. Okay. So you make one Python file. Okay. Okay. That has both functions, sine d and cos d. Okay. So these functions aren't doing much. Now you need the standard cosine functions. So make sure you import. Once you okay, so get working for being a number, then try your function out on an array and let me know what happens. Okay. Okay. All right. So this is something you can try during the day or during a break or whatever, because I'm still going to continue with all this. But okay. Yeah. Oh, this line? Oh. Oh, okay. Right. So what's happening is this. So really, this file is interpreted like as a shell script, and so the # exclamation point indicates what program is actually being used to execute all this. So I remember long ago when I first learned about shell scripts, I would do this in sh or some other command shell. So the idea is this would be the first line of your file. You'd write your script, and then it would be fed as input to this and run. So here it's being fed to this program instead. So the idea is so this executable with this parameter is used to run this.
And if we don't have that in there,
Then yeah, it probably won't run.
I'm getting like the module now.
So what might be so? Okay, if I try something similar. Okay. Okay. So if I go ahead and delete this line. Oh, that's strange. It didn't give me any error or anything. But if I run it in here, well, there's no code to run, but okay. That's weird. Unless Okay, I think I'm gonna load a different one. One that okay. Try Newton's square root from last time. So I'm gonna see if this works, and once if it does, then I'll explain. Um, okay. Now here's what I did. Now before I would run it this way. Type Python and then Newton square root dot pi, and it would run. But here's what I did. Up here, I changed the permissions of a file to make it executable. I honestly don't know how you do that in Windows. This is a Unix thing. And then what I can do is I can run this as an executable script. And that's where this line is important.
So that's just because you have
What?
that line for Unix.
Right. So I don't know if Windows evolved to a point where it's going to read that and figure out how to run it, but yeah. it's basically it can be run like any other script. So in a script in Unix, the first line tells you how you want the script interpreted. Right, yeah. Yeah, because also, if you pass it to Python, like the other way of running it, like I did right here, then yeah, Python is going to load it and interpret it.
So I'm getting this command after Flash. I've saved it. It's pretty much exactly what you have.
Yeah.
And I tried to say from convert 10 or convert 10. And it says module not found.
Okay.
So is that a directory?
Yeah, it's not able to find the file. Okay. So now, are you also using Spider or? Okay.
Yeah, and like all the other files I've been using all this time, I created it and found it. I saved it in that place, found it.
Okay.
Like all these other files. They were
Oh, okay. Well, yeah. Now, is that this directory? Okay.
so change that to where I am.
Right. Yes, you can see that. Yeah, exactly. I have to remember to do that when I start my session. Okay. Alrighty. Now, so I have a more complicated function, but I'm going to walk you through. Okay, vec angle 2. So the purpose, as described here in my documentation, is given x and y, which are assumed to be vectors of the same length, so one-dimensional arrays, and then it computes the angle between these vectors in degrees and radians. So this is as an example of multiple inputs and multiple outputs. So as far as how the function proceeds, so first here's a formula written mathematically that we're using the fact that the dot product of two vectors is equal to the magnitude of one times the magnitude of the other, magnitude in the two-norm sense, so the Euclidean length, times the cosine of the angle between them. So what we're going to do is compute the dot product, compute the two norms, divide, to get cosine of theta, and then just take an inverse cosine, and that will give us the angle between 0 and pi. Okay. Now, so what we have here is, first we do some idiot proofing. We get the length of x, how many elements there are, and then we make sure that that is equal to the length of y. And here, if they're not different lengths, then we have a graceful, well, semi-graceful exit, or at least we allow for possibility of a graceful exit, that we raise an exception that the vector legs must agree. So this is my own error message that will be printed. What this statement does is it creates an exception object, and the function will exit where this exception is thrown. So Python, like C++, has exception handling, which is not something I'll get into today, but I'll cover more later, where other code that calls this function can catch this exception and then arrange for some graceful exit or continuation of whatever code it has. So this is a better way to handle errors so that you don't just have some god-awful crash that somehow the program could continue and in some, as much as possible anyway. Okay, so we need to compute the quantities up here. We need the dot product, and then we need the magnitude of both. So we have dot, which we've seen before for matrix multiplication, but if you just apply it to vectors, it just computes a dot product. So if x and y were matrices, it would compute dot products of all possible rows of one and columns of the other, which is matrix multiplication. But here we just compute a number, the dot product of these vectors. Then, here we have the linalg submodule of NumPy, where there's a lot of linear algebra functionality that we'll be seeing more of. And in there is a function norm. So you can use that to compute the norm. So like in MATLAB, the default is a 2 norm for vectors, but unlike MATLAB, the default for matrices is a Frobenius norm. Does anyone remember what the Frobenius norm is of a matrix? Those of you who took 561 saw it then. No? What?
Was it an interval?
No. Oh, that's something else. Yeah, that's our iterative methods. That's a square. It's a square root of sum of squares of all the entries. Is a Frobenius norm. Now, I actually prefer that default because it's efficient to compute. Whereas in MATLAB, the 2 norm of matrix is the same thing. So for a vector, 2 norm and Frobenius norm are the same, square root of sum of squares of all the entries. But the matrix 2 norm is the largest singular value, which needs to be computed by an iterative method. We don't want to do that unless we really, really need to. So at least for vectors or matrices, both our choices are easy to compute. So in other words, whatever you give it, vector or matrix, it's the square root of sum of squares of all the entries. So we go ahead and do that for x and y. And now, by taking the dot product divided by norm of x, norm of y, which we do here, we get the cosine of the angle between the vectors. And then we've already imported math. So now we use math.acosine. So that's short for arc cosine or inverse cosine of the angle. And that gives it to me in radians. And now I convert to degrees. So I, in some sense, gave away what I gave you to do. But so now we have the angle in both forms. And notice I use math.pi for pi. And now for returning, I want to return both of them. So I return angle in radians, comma, angle in degrees. Um, so now to call this function, well, I have a vector. Well, actually, I have a vector x and a vector y already. So I'll just go ahead and use these. So I want angle in radians, angle in degrees equal to. Oh, wait, I need to import this. Okay, now I can do this. Angle in radians, angle in degrees equal to vec angle 2 xy. Okay, so there's the angle in radians, and then the angle in degrees. Okay. Now, I'm going to intentionally call this incorrectly. I'm going to take only a portion of y. So now x and y. What? Yeah, this is a not equal operator. Remember when I went over those relational operators last time?
Yeah, I just couldn't see what it is. So
What?
I couldn't see, so I was asking to tell what it is.
Oh, you can't.
I don't mind.
Oh.
Just can't see. It's not my fault. It's not the screen.
Okay.
It's my eye. Yeah.
Okay, well, that's good enough. All right. So now I have vector of length 5, and this is a vector of length 2, because it'll be elements 0 and 1. So this will create an error message. And sure enough, it does. So you see all this gobbledygook associated with Python error, but this is my error message that I put in here. Okay. All right. So any questions about how this function does its job? Okay.
What if you had different errors, like more than one error? Just a different statements?
Okay. So yeah, you would have a different raise exception statement for each scenario that creates an error, and then whichever one comes up first, that's the one that's thrown. So then you can have informative error messages, which is funny because now we have a lot of languages have exception handling, so there's the opportunity to handle errors in an informative way, and yet a lot of languages still don't do that. You get these error messages, and like, I don't know what that means. Take LaTeX, for instance.
Oh, good heavens.
Yeah.
I mean, it'd be more meaningful if they put it in Chinese.
Yeah. Okay. Let's see what's about this function. All right. We'll take our first break at this point. See if you do those simple functions that I gave you earlier, and then when we come back, I will get into graphics. Okay, we're back. So, questions about anything from the first segment? Everybody converting temperatures to converting degrees to radians? Okay. Well, so I want to show you what's going on here. Actually, no, not yet. When I come to another example, well, what you would see, those of you who tried it, I know Brianna did, after you got it working for computing sine or cosine in degrees for a single scalar, just fine. You try it on an array, and it doesn't want to do it. Yeah. So that's one, I could think, major disadvantage of Python math functions compared to MATLAB. That they're not able to work with arrays just all in one shot. So if you have some vector or matrix and you want to apply a function like exp to every single element of it, you have to do the loop. But there is somewhat simpler way to make that happen, and that's something I'll come to as I continue through this tutorial. Okay, but first, something more interesting, more appealing: graphics. Now, to get form graphic operations, excellent package for that is matplotlib. So I'm going to import matplotlib, but not matplotlib itself. I actually want a sub-package of that called pyplot, pyplot. Now, that's kind of a long name, kind of a pain to refer to in every function I'm going to use. So I'm going to give it an alias. I'll just make it plt, for short for plot. Okay, so now I can use like plt dot to refer to any functions that are in this submodule. Okay, so what I want to do is, let's say something simple. I want to plot like y equals x squared. So I'm going to make a vector of x values from -1 to 1 with a spacing of 0.001. Now, unlike functions like sine or cosine, if I want to square a vector, that I can easily do. The exponentiation operator is defined for vectors, so I can do that. Whereas if I was doing this in MATLAB, I'd remember to use the dot. I'd have to do y equals x dot up arrow squared. So at least something's more convenient in exchange for other things being less. So now if I want to do like plot xy. Oh, whoops. Forgot my sub-package here. plt.plot xy. And it shows it shows a plot here. Now, when I write code in here that does plotting, and actually I'll go ahead and do that in just a little bit. It can actually, like if I'm doing it in this environment, it will show it right here in the console, which you might not want. But if I run it outside as like from a command prompt as a script, it'll show it in a separate window, which is likely what you would prefer. But one that's nice thing here is once I have my plot, I can right-click on this and I can save it as an image. And by default, I've saved some images already. By default it'll save it as a PNG, portable network graphic, which is actually the format I use for like papers and presentations and such. Okay, so at least it's something that's savable. But what I want to do now is create a new file. Wait, I don't want this. Okay. And I'll just call this powers of x. Okay. So I'll go ahead and import this. Okay. And what I'm going to do is I'm going to carry out one of the problems in here to reproduce a plot that's here in this book. And that plot is right here. So I'm plotting x squared, x cubed, x to the fourth in different line styles. I have a title for a plot, and I also have axis labels, x-axis, y-axis, and a legend over here to indicate which curve is which. And here in the book, they made me do it black and white. But I'm going to have colors, different colors for different curves. So like blue, red, and black for x squared, x cubed, x to the fourth. Okay. So the way I will do this is, okay, so I need my x vector. Well, so I also need numpy to create my x. Okay, so now I have the same commands as I had before. So now I can do plot. So I'm applying it like before, but I'm going to specify explicitly, and this works just like MATLAB. So in single quotes, you specify blue, and the single dash is a solid curve. But another thing I'm going to add is label and a quoted string to indicate x squared. Later I'll make a legend, and if I found the easiest way to make a legend is to specify the label up front when you plot the curve. Okay, and then I can do the same with x cubed. Make it a red dashed curve. I'm gonna make here. I'll put the MATLAB equivalent. Okay, x cubed. So MATLAB equivalent is plot x dot cubed. Okay, and then why is it still complaining? Okay, I want x to the fourth. I'll make that a black dotted curve, and that syntax is the same as MATLAB. So I guess I try to make it as much like MATLAB as possible. And we see the commands are very similar. Okay. And then label for the x-axis and y-axis. Again, much like MATLAB. Okay, and then I want a title. Okay, and then here, legend, which if I was doing this in MATLAB, I haven't specified the labels yet. So I'll do x squared. So I put all the labels down here. Okay. Now, let's see what happens when I run this. Okay, and we see the curve there. Now, but I want to do the same thing here from the command prompt. Whoops. Okay. So I'm going to do Python powers of x. Okay. Notice, nothing happened. We didn't get a window. It's like, oh, did I do something wrong? And yes, I did actually. And this time I can actually say it was intentional. For running the script, you need this command. Once you've put everything in the plot that you want, use this command, plot plt.show, and that will actually display that. Now, in running it in the console, in this environment, it doesn't matter. But here you do need that. So now run it again. And there it is. And notice it's displayed in a separate window. And here I notice the old 3.5-inch floppy disk icon. Yeah. So I can use this to save it again as notice it as a .png. So I won't do that here. And then notice that this is generating some messages. Not sure what that's about. That's kind of annoying. But once I close it, then the script exits. So that's one thing to keep in mind, is that when you display a plot, then your Python script is waiting for you to do something with that window before it continues. Okay. So at least we have some basic graphics operations going. So one thing that was interesting here is that I didn't have to do a hold on or anything. I just kept adding these items to the plot, and it assumed that I wanted them all on the same plot. Now, Actually, one thing I'd like to check here, because suppose I wanted to no longer do that, like maybe have a fresh plot. Okay. Okay. I wonder if we have somewhere that's convenient a list of all the commands. Okay. Oh, yes, they do. It's not like a list. They're all on this page. Wow, that's exhaustive. It'd be nice if we had like a list somewhere. Okay. And okay, so you can do close, and that would close down a figure window. That would certainly do it. And okay. Oh, they used to have a hold command. Okay. Yeah. So here, the default behavior is the opposite. That's what this is saying. The default behavior is opposite of MATLAB. So MATLAB's default is hold off. Like you plot something, it wipes out what was there before. Here, the default is to leave it there. But yeah, these particular commands are going away. Okay. So .cla is clear the current axes. So I'm going to try this. I go ahead and show this. And then I clear everything. So clear axes. Oh, so if there's clear axes, I'll bet there's also a CLF to clear a figure. But I only have one axis. So then if I go ahead and plot x, let's say x to the 8th in green, and then show it. All right, let's just see how that behaves. So, all right, there's the first one after the first show command, and then I exit out of that, and now here's the other one. Okay, and notice they're both called figure 1 because I only cleared the axes and I'm using the same figure. Now it's plotting it in green, and then I exit. Now, as far as if I want multiple figures, oh, okay. It'd be nice if there's a list so I could like browse through the list of commands instead of having to scroll and find out where they are. Okay, so right. So yeah, so just like in MATLAB, you use a figure command to create a new figure. So plt.figure would create a new figure, and it actually return it. So if I want to plot things in different figures, like have a figure 1 and a figure 2. Okay. All right. But then I want to be able to work with each figure object. So okay. So for example, All right, let's try this. I want this to be figure 1, figure 2. So now I don't need to clear this anymore. But I use plot.figure. And notice the default is to auto increment. I have a figure 1 already. This will become figure 2. Or if I can specify a number, if I want to, I can specify a number if I want to do that instead and override it. But here I'm content with it being figure 2. But I need to save it as a variable. So this is the new figure object that I'm getting. And okay, let's see if that works as far as creating a new figure. I need to show it. Okay, I'm already showing it. Okay. Okay, it did not like that. Okay. Still made it figure 1. That bugs me. Okay. So if I tell it I want figure 2, figure 1. Okay, so I can give it a new number that way. But I like to be able to work with different figure objects at the same time. So if I make a variable for figure 1, okay, and presumably this becomes the current object, but now I go to x to the 5th in green in figure 1. Okay. All right, so there's figure 1. Although now I'm going to close it, which, okay. Cannot put single artist in more than one figure. Interesting. And it's complaining on this line. It did not like this. Okay. So if I put a show statement after each one, will it prefer that? There's figure 2. And it still didn't like that. And maybe because I closed the first one. Sorry, this is this is what I get for going off script. Yeah, because in MATLAB it's very easy to like mix graphics operations. To like I want to do this in this figure, then I want to do this in this figure, and come back to this one, and it doesn't really. You just have to tell it like which figure is. Well, you do have to say use the figure command to indicate which figure is the current one. Okay. So that's probably what happened here. So it's thinking figure 2 is the current one. So in fact, if I get rid of this, these statements, then all right, figure 1 and figure 2, and there's no error. But now what happens if I run this from within here? Okay, here it doesn't give figure labels at all. That only happens when it's in a separate window. But you get both of your plots. Okay, so just playing around with that. All right. Now, okay, but at least we have the basics of plots, and very importantly, being able to save them as a file for inclusion in like a paper or presentation or something of nature. Okay. Now, all right. So, I suppose the basics of graphics. Although I will do some more things involving graphics in a little bit. But first, functions for working with polynomials. Now, you may recall that in MATLAB, you can work with polynomials as a row vector of their coefficients, and do things like computing roots and derivatives, integral, antiderivatives, things like that. And actually, all of that works essentially the same in Python. It's just a matter of a different syntax. So I'm going to use some commands here. This is from NumPy with the various polynomial commands with MATLAB equivalents. So for instance, the vector 1 minus 3, 2, 0, 2, comma 0, not 20, represents x cubed minus 3x squared plus 2x. So that convention is the same in both MATLAB and Python. So from highest degree to lowest, from left to right. So if I do this, np.roots with that polynomial, so this polynomial has roots that, well, 0 is a root, and also 1 and 2. So sure enough, it gives the roots as floating point numbers, so 2, 1, and 0. But to go the other way, so I'm going to do that again with a MATLAB equivalent. Okay. Now, going the other way, there's poly. So if I have a polynomial, I know the roots 0, 1, and 2. And I want the coefficients of a monic polynomial, in other words, leading coefficient 1, that has those roots, then I can do that, and sure enough, so roots in poly are inverses of each other, except for error, floating point and otherwise. Okay. Now, you also have a polyval function for evaluating polynomials. So, for example, if I have a polynomial 1, 0, 0, which is x squared, and I want to evaluate it at the numbers from 1 to 10. So that's a range from 1 to 10. So that's equivalent to polyval 1, 0, 0 from 1 to 10. So that gives me an array of, now a range by default with these integer values gives integers. So all of these squares are also integers. Okay. So now if I want to, dang it, derivatives. So polyder. So that's equivalent to MATLAB's polyder that computes the coefficients of a derivative of a given polynomial. So derivative of x squared is 2x. Now, one thing that's a little different. Well, actually, I wonder if MATLAB offers this. I'm going to take a look at MATLAB's polyder. Oh, okay. Yeah. So so what happens here is polyder in MATLAB is only useful for computing a first derivative. but I can use Python's polyder to compute higher order derivatives. So if I want, for instance, the second derivative. So by default, it's the first derivative. Here, this is second derivative. But if I want to do the same thing in MATLAB, I have to call polyder twice. Okay. So that would give me, so second derivative of x squared would just be 2. So that's a optional second argument. Now, just like with MATLAB, it's polyint. That computes the coefficients of the antiderivative. So what you call is the same. So here we're assuming by default a constant of integration of 0, so you're plus c. So sure enough, antiderivative of x squared would be 1/3 x cubed. And finally, for polynomial multiplication, MATLAB offers conv, which is convolution, because that operation happens to be the same. But Python, we call it by more intuitive polymul. So for instance, if I have x squared and x, then that would give me x cubed. Okay, so that's a rundown of the polynomial functions of our MATLAB counterparts. So computing roots, computing coefficients, evaluation, different derivative, antiderivative, and product. Okay. Actually, when I post this later, I'll go ahead and explicitly label these in the history log. Okay. Now, so I have a somewhat more challenging exercise to do with this, polynomial functions and graphics functions. Okay, yeah, this one right here. Okay, so you're writing a Python function called graphPoly. So it accepts as arguments an array that'll be a polynomial, coefficients of a polynomial, and then two numbers a and b, indicating an interval ab. So the first task that's involved is you just create a vector of x values between a and b, equally spaced. Using like a range or linspace. I don't really care how many, so you might as well use linspace. And then you can use your polynomial functions to plot the graph on the interval AB. So using the plotting functions I was just showing you. So that's task number 1. The second task is you go ahead and compute the roots of a polynomial, and then you go. Now that's going to give you a one-dimensional array, a vector containing those roots. So then you go through the roots, and you figure out which ones are real. And so then you plot the roots, the real roots, only the real roots of a polynomial, on the x-axis using red circles. So how you do red circles is the same as in MATLAB. So you indicate red and then you use the O to indicate a circle. So that'll show up on the same plot. So so what you can do is you can check the imaginary part. Now, I showed you that last time. So for example, okay. So I'm going to make up a polynomial here. I want to see if this will work on a list. Well, actually, it does work on a list because these are not arrays. These are not NumPy ND arrays that I'm passing. as arguments for just lists. So it's a list of coefficients. So I'll make up a polynomial that has a complex roots. X squared plus 4x plus 9. So NP roots of P gives me an array, and these are of a complex roots. So I'm going to save those in a variable, r equals. And now that is a NumPy ND array, dimension 1. So now if I do r dot real, that gives me the real part, and r dot imag gives me the imaginary part. So once you have this array of roots, you can have a loop that examines these roots, like really you're going to examine the imaginary part, and if it is non-zero, then it's a complex root, and you can ignore it. But if it's 0 or negligibly small, so let's put a criterion here. Consider a root to be real if the absolute value of the imaginary part is less than, let's say, 10 to the minus 12. Let's pick an arbitrary cutoff there. Okay. Use a loop to examine the roots. Use a list to store the real roots. So I'll help you a little bit with that part of it, since we haven't really talked about list operations very much. So for example, initially, I'll use this RR, real roots, would be a square brackets list, and then to add to the list, you can use the append function. So if I want to add a number to the list, then this will do it. So because if you have a polynomial degree n, and roots will return n items, you don't know how many of those are real. You just have an upper bound. So you're just going to be building a list with whatever roots you find that turn out to be real. Okay. So then you can pass that list of x values to plot. So you're plotting. So the x values are the roots themselves. So y values are all zeros. So once you have the real roots, then you need to create an array of zeros to plot with them. All right, so that's something that'll be a bit more challenging than other things I've given you. Okay, 12:15. Okay. All right, so right now I'm going to keep going, but then it will come up to a break period at a certain point. We'll see. I start off again at 12:40. Okay, I'll go a little further, but we'll have a break coming up soon. Okay. So as far as files go, put your code in graphpoly.py, call your function graphpoly, and then from graphpoly import graphpoly to actually have your function available for use. So example usage. Here's a polynomial that has a mixture of real and complex roots, the cubic, plotted on the interval 0 to 3. So you can try testing it that way. Okay. MATLAB has a concept called anonymous functions. For example, in MATLAB, what you would do is I could define a function f that's a function of x, and it would perform, like in this case, I want e to the sine 2x. So how would I do something similar in Python? You can, using a lambda keyword. So I can define a function f equals lambda, x is the input, and then a colon, and then here's what I wanted to do to x, is e to the, math.exp, math.sine 2x. For some reason I noticed I didn't have math.exp. Maybe I'd already imported exp. Okay. Actually, now that I think about it, if I try this right now, yeah, it won't work because I haven't imported math yet. So now that I've imported math, then I'll know what to do. Now, so sine of 2 times pi over 4 is sine of pi over 2, which is 1. And e to the 1 is just e. So it prints that out. Now, the main benefit of doing this is I have a previously defined array x. Okay. I'm going to make a shorter one. Okay. I made random temperatures earlier, so I'll just use that because there's only 5 elements. So if I do f of x, oh, it doesn't like that? That's really weird. I really thought it would do that. Oh, that's so aggravating. Yeah, okay. So this is good for computing, for making anonymous functions like in MATLAB, but you still have the same limitation of the math functions that you can't call them on arrays. Now, what I could do instead is let's see if it'll take this. Excellent. Okay, that it will do. So here's a relatively quick way to apply a given function that is intended to work for numbers and apply it to every element of an array is using an applied loop here. So I have, so this is quite one convenience of Python. I say I want this list, so the square brackets define a list of f applied to each element of x, where I define the subscripts using its for loop for I going through range of up to the length of x. So in other words, all indices starting from 0 up to however many elements there are minus 1. So that covers everything. So if it's something you can do to, at least in a single statement, without having to define like an explicit for loop with like multiple lines. So here you can do this all in one line. Now what comes out is this is a list of elements. It's not a NumPy array. So x, on the other hand, x is an actual array. Y is a list. But I can make it into an array if I need to. So now it has the same form as x, if that's something that you really wanted to do. Okay. But yeah, it's kind of aggravating that it's not as easy to apply these math functions to vectors or matrices as it is to in MATLAB. I can also define an anonymous function of multiple inputs is easy enough. I want a function that takes 2 inputs x and y, and compute the square root of x squared plus y squared. So then g of 2, 1. So be a square root of 2 squared plus 1 squared, so this is the square root of 5. So, so as long as you keep the order consistent, then all of that works. Okay. We'll take a second break at this point, and then we'll see how you guys do with. Oh, wait. No, wait. Okay, not for a break. Okay, so we'll see how you guys do. So what I'm going to do is, I don't have much left in a tutorial. Maybe we can get through that, or maybe a battery won't run out, and then the remainder, if whatever time remains, we can talk about what I assigned you. But I'm going to show you a function. It's also for graphing a function, but not a polynomial. So it's still somewhat distinct from what I just gave you. Okay. Of course, now my screen is too dark to read, but okay, graph func. Okay, so the purpose of this function is just taking any function f, not necessarily polynomial, and graphing it on the interval AB. So I make a so what I do is I use linspace to create a vector of equally spaced values between A and B. And then, this is convenient, I want to make a vector y, 0 vector, that has the same size as x. Now MATLAB I would do like zeros of size of x, but I could say zeros underscore like to achieve the same effect. So now I don't care what size it is, this will be the same. Okay, so that's convenient. Now, since I can't just call my function f on the entire array of values in x, what I do is I just use a loop. Now, fortunately, that's not necessary for polynomials. Polynomials, polyval will take arrays, but a general function won't. So I have a for loop going through all the indices in x, like I did earlier, and then I just plug in each element of x individually into f to get the corresponding y values. So now I have vectors of x values and y values, and then I just go ahead and plot this and show it. So for my function f that I defined earlier, well, okay, I can't call definition from here, but if I go back for my commands, this is a function here, e to the sine 2, e to the sine 2x. So that's the function I want to plot. So I can just do, okay, so I want to import this. Okay, so now I can do graph func f, and I'll just use the interval 0 to 3. And there's a graph right there. Okay, so so this is how we can. Now, what's interesting is notice my variable f. I can just go ahead and pass it. I didn't have to do anything funky like using, in MATLAB you have to use an @ sign in front of functions to tell if it's a function. But any function handle in Python, you can treat that as a variable without any special syntax. You can just pass it and it knows what to do. Because in here I just call f of whatever x I'm passing to it. So that's convenient. But you can just pass functions around just like anything else. Okay. And later when we get into, I guess we're going to spend some time soon, like next week, talking about numerically solving ODEs. where we have to have a function that defines a time derivative, and so we have the same mechanism for that. Okay. Now, how's my battery doing? 16%. Wow, it's going down fast. Okay, so some of these I've mentioned before, but I just want to have them all in one place. All right, so okay, to demonstrate these, I need to create some variables here. All right, so like a 2x2 matrix. Okay. Okay. So for instance, a dot shape is the same as size of A in MATLAB. So in this case, a 2x2 matrix. Length of B. So for vectors, there's an equivalence there. Now, A dots there's an attribute of A called size, and that is equivalent not to size of A, which I just showed you, but the total number of elements. So for a matrix, it'd be number of rows times the number of columns. So 4 in this case. Okay, you can reshape matrices. So for instance, I'm going to make a random 5x5 matrix here, and I want to reshape that into a vector of 25 elements. So it's a little more complicated here. So if I do reshape B just the simplest usage right here. And this, what this will do is this will actually overwrite B. Now, as far as what this is equivalent to, let's take a look. Sorry, I should have shown you what B was like first, but now B is... All right, I have to do this again. First, I need to show you what B is. All right, so here are the elements, and now I will reshape it. Okay. So notice what it does. It takes all the elements in the first row, then second row and so forth, like 0.610, 0.348, etc. Now, I'm going to do a similar thing in MATLAB. I'm going to create a random 5x5 matrix. All right, so here's my 5x5 matrix. And then reshape it to a 25x1 vector. I need to make this a little bigger. Now, if you look at the first elements, how is it reshaping? Yes, you described that, yeah, by column. So notice the first elements are a first column, second column, third column. Yeah. Now, why is that? Here's why. The convention used in C is store by rows, also known as row major order. The Fortran convention, store by columns. And MATLAB is, the lowest level functions in MATLAB, like basic linear algebra subroutines, are implemented in Fortran, whereas Python is built on C. So defaults tend to go with a C convention in Python rather than the Fortran one. So that's one thing to be aware of. It could really be a gotcha for you. So if I pull up the command I just did here, this command is actually equivalent to reshape a MATLAB command. Okay, B equals, because now B transpose 25 of 1. Okay. Now, the other thing is Python's reshape is destructive. MATLAB's is not. Now, what I mean by destructive, that's my words, not official by any means, is it modifies what you're reshaping, whereas MATLAB returns that as a new entity that you can assign to something else. So, like here, for my MATLAB equivalent, I had to do b equals reshape, whereas here it just does it in place. So be careful about how you use it. Okay, so if this is how it behaves, what if I really want the other way? Like in MATLAB, I want to store my columns. To do it in Python, fortunately that's easy to do. If I do b, the shape I want, and then a third argument, an f in single quotes. So that says Fortran convention. So that does the same, it's equivalent to b equals reshape b25, 1, without the transpose. Okay. So beware of your ordering, the storage of matrices is very different than what we're accustomed to in MATLAB. Okay. Now, the sum command works similar to MATLAB. So what it does is it sums each column. And produces a 1D array of column sums. So 2 and 1 is 3, 3 and 4 is 7. Now, alternatively, NumPy's sum. Whoa, put up a whole help page there. I didn't want that. So this will do the same thing along axis 0, which corresponds to the rows. Or in other words, it's summing. Wait, it's going through the rows to produce column sums. To sum rows, similar syntax. Stop that. Okay. So that will sum each row and give you 1D array of the row sums. So axis 0 refers to rows, axis 1 refers to columns. In this case, the axis it's telling you which axis to sum along. Okay. Okay. But if I do np sum with no axis specified, that will sum everything. So for matrix, it's like calling sum twice. So it just sums up all the entries and gives you that single value. Okay. Okay. So questions about these helper functions? Okay. Now, saving and loading data. So in MATLAB, you can use the save command. It writes it into a .mat file, and then you can use load to bring it back. So you can do something similar in Python. So I could do this. NumPy. So NumPy provides these. Save z. Writes it into, so make a file called test or mydata.npz. And you tell it what variables you want to save. Now what this does is it's saying save A as A and save B as B. If you want, you can give different names, but the names on the right side have to be variables that already exist in your workspace. And if you want to save them under different names, you certainly can. I'm just choosing not to. So this is equivalent to save in this file name and then a listing of variables. So this is a MATLAB equivalent. So now I can say A equals 0 and B equals 0 to wipe them out. And then I can do Now if I do this, I can load the same file name. So that's equivalent to data equals load that. So now I can use these names that I gave on the left side of equals, A and B, as indices into data. So I can do data A. So Python allows different forms of indices. So that's the matrix A that I saved earlier. And then B is also what I saved earlier. Now, so now what I want to try here. Oh, you know what? I think I might have said something incorrect earlier. You know what? I did. Python's reshape is not destructive. Notice when I did this, it didn't modify B. It output this. Okay, so sorry, that's wrong. Not sure where I got that earlier, but okay. Okay, so it behaves the same way as MATLAB. You can save it into a new variable. This is what tipped me off that this was still a 5x5 matrix rather than a vector. Okay, okay, so my Python equivalents or MATLAB equivalents. Okay, so there's no B equals there. What happened here? Hold on. What's B? Oh, I see why. I showed these, I didn't save them. So here's how I can actually restore. Dang it, sorry. Okay. All right, so I just want to redo these commands so I have it in the history log correctly. And then I had the other one with a transpose. Okay. This is what I hate about teaching, is that your IQ drops by 30 points. And like I did this a few weeks ago. I was like, I forgot it all. Okay. Now, on the other hand, suppose I try this. np.saves. And I don't specify any variables. That's okay. I'll make sure my syntax is right. np.saves. Yep, did all that. Okay. I think I know why, but I need to check in my folder here.
What's a pickle?
I have no idea. Hadn't seen that before. Okay, courses. Okay, battery's down to 8%. Okay, there is a file created. Okay, but maybe it's because there's nothing in it. Because MATLAB by default, if you do save, it'll save everything. But notice here, this is a one I saved previously. That saved A and B, and there's 682 bytes. Here is 22. So the default is to save nothing. So that's kind of unfortunate. So MATLAB default of saves, save everything. Python default of saves, save nothing.
I'm sure that when Python was not a direct opposite reaction to that, I'm sure it was like the
I know in certain cases,
but
yeah.
it's just the C versus the workaround.
Yeah, that's one thing. Yeah, because there's other things like where it seems like it went out of a way to make it as similar as possible, like polynomial functions and plotting for graphics. Yeah, so go figure. The last item I have in the tutorial, which is now I've done 7%, measuring efficiency, at least in terms of computation time. If I import the time package, I can do this, like tick, and that's MATLAB has tick and talk. I'm just using the same names as a coincidence. So I'm recording the current time, and then carry out a matrix vector or matrix multiplication, and then time again minus tick, so I can subtract time values. Oh, okay. Well,
I'm so sorry for confusing.
okay. Yeah, I'm down to
Thank you.
7%. Okay, well, class is over in 15 minutes anyway. Okay. So just, now I know I won't go dead in the middle of class. Okay, next. Okay, great. Yeah. Okay, so now, well, 46 seconds elapsed between the time I typed tick. But if I were to put this in a script where it would do everything all at once, so actually I can do multiple statements using semicolons. So I can do, I'll save this in a variable, and then talk equals time minus tick. So I do all that at once. Okay, yeah, that's about how much time it should take to multiply a 2 by 2 matrix, on the order of 10 to the minus 5 seconds. So, okay, so returns the current time. So actually, if I print out tick, so you can subtract. So you can perform arithmetic on those times. So if you look at tick, that's a pretty large number, which I'm guessing it's the Unix convention, where time is measured as like time since like midnight on January 1st, 1970 or something like that. Well, if I do, well, that's close to 50 years. 365 days times 86,400 seconds per day. Okay. So yeah, that'd be the number of seconds since that time.
What's significant about the date that they're referencing?
Probably chosen arbitrarily, but it was all of that was being invented around that time, which is probably why they chose it. And so what's interesting is, since that's been in use for a long time, so that's how I knew that Y2K wasn't going to amount to anything, because computers were already using that to measure time. Windows uses a somewhat different convention, but similar idea: time since a certain predefined date. So Unix and Windows never stored dates internally as like a 2-digit year. They had functions to convert this kind of value to a human readable date. Now, certain software on its own could use whatever time representation, and they may have messed up that way. But generally, if you're using the native date time functions, you wouldn't have a problem at all. Now, there will come a time, like around middle of the 21st century, when this value, number of seconds since 1970, will no longer fit into a 32-bit integer. And then there might be a wraparound problem. But I would imagine that around the year 2050, that nobody's using 32-bit anymore. We're already using 64 bits, pretty prevalent. So I think that's why no one is thinking that that'll be a problem. But yeah, okay. So I've gotten through all the tutorial stuff. So at least now we can move on to more substantial things. So for the remainder of the time, I want to see about any difficulties anyone has with what I assigned earlier about plotting a polynomial and also plotting the real roots. Okay. Well, first, was anybody able to pull it off?
No.
Okay, good. All right. Yeah. Does anyone have any questions?
I could look back at the saving data. I'm having
Oh.
just a little bit.
Yeah.
A little bit higher. I think I'm mistyping something.
Oh. Okay. Where'd it go? Okay.
Yes. That's the problem.
Yeah. Okay. Alrighty.
Yeah, using parentheses instead of brackets will cause problems.
Oh, okay. Alrighty. Okay. So, any questions about anything? Okay, I'll stop the video at this point. Of course, it takes so much work to splice them all together. But I'll stick around to 1:15 in case anybody has any questions.